Come on in, everyone. All right, got more people coming in. Got a couple more minutes, but you are welcome to ask me questions while we wait. Come on in, everybody. Still waiting. Now it's time to start, but I want to make sure everybody gets here. Does anybody have any questions before we get started? All right. Well, I guess I'll go ahead and get started. It is time. And I accidentally will let my students go at 20 after the hour. So keep an eye on that. I'm so used to teaching my day classes and they always end at 1:20 or 3:20 or something like that, that I inadvertently have twice in the past and told everybody class was over and it was only like 6:20 when it was supposed to be 7:40 or 6:40. So if y'all can help me with that, that'd be great. Help a senior out. Anyways, it looks like no one has any questions. I hope y'all got some understanding about how charges can induce charges and other things, how they can polarize them, how they can actually make them actually charged, net charge other than zero. Those videos I think should have been helpful to you on that. You can also do some other videos if you just want to Google search for Van de Graaff generators or Spark demonstrations on YouTube. You'll probably find a lot of different videos that are helpful. One thing I didn't get to do is I did a simple calculation with Coulomb's law, and it was just for 2-point particles computing the force. But the big thing with Coulomb's law and with gravity for that matter is that it provides a vector, because he gave a very specific description about how the direction of the force could be determined. But basically, just like in gravity, if you assume it's 2-point particles, then the force of attraction in gravity was a constant g times the product of the masses, and then divide that by the square of the distance between them. And Newton told us that the force is always attractive and that the force acts along a line connecting the particles. Well, in the event that it wasn't actually particles, actually they were continuous bodies like a ball or something, then you're supposed to find the center of mass of each of those objects and find a line that goes to the center of the center through the center of mass of each of those objects, and that line will be parallel to the vector force. Again, remembering that they're always attractive forces in gravity. Well, we had the same thing in Coulomb's law, where F is equal to K Q1 Q2 over R squared. But the direction it point can be, well, for sure it can be a attractive or repulsive or repellent force, meaning like charges repel and unlike charges attract. So you've got to sort of decide a priori which way is it going to point. So what you do is you imagine, if they're asking you for the force on one, you look at that one particle and realize that the line going through it and going through the other particle makes a parallel line to the actual force. Then you got to say, well, if it's attracted to it, then it's going to pull it towards that other one. If it's repelled by it, then it's going to push it away from that other one. So that's how you work it out. Again, that was for point particles, but in this case, if you don't have a point particle, you actually have a ball or a kidney-shaped charge or something. What you do is go about some process whereby you could calculate the center of charge of the object, which is often, I mean, unless it's got a weird distribution of charge, it's often the same as the center of mass, but it could have a weird distribution of charge. The good news is we're not going to deal with those little intricacies very much. You can also take the center of the sphere, if a charge is distributed over a sphere uniformly, whether it be on the surface or in the inside throughout, uniformly distributed, then the center of the sphere would actually have the line going through it. So then you just use the center of the spheres if you're wanting to do that. So we're going to try to continue with this Coulomb's law, but using continuous bodies. So to do that, we're going to pretend like atoms are infinitesimally small point particles that we can sum up in a Riemann sum type scenario. So before we do that fancy stuff, I'm going to go ahead and show you one surefire way to actually compute a vector using this formula. And this is one I didn't do with my daytime class. I've done it in the past, but I think this might be helpful for you guys. So does anybody have any questions now before we get started? Hopefully you saw that the syllabus is up. I'm still tweaking it. I found a bunch of typos, so you'll see later other versions of it go up, but it's essentially got everything right. It's just a few missing things here and there. Remember, our online test will be online, open book, open notes, open any other book, open internet searches, but the face-to-face tests, the midterm and the final will be proctored, or you at least have to have your own computer with a webcam that can access Canvas, can run Canvas, can use Respondus lockdown browser and Respondus monitor as well. So hopefully y'all just don't have any questions. I keep asking if you have any questions, you don't say anything, but everybody's muted, of course. If you need to ask me a question, go ahead and speak up. So what I'm going to do now is I'm going to attempt to share my screen. I'm going to attempt to share my screen. There it is. All right. So now I got to do this, turn on this. There we go. All right, so now I've got my screen sharing. Now what I'm going to do is imagine some particles, and I'm going to put it in a coordinate system just because you can always make a coordinate system, and sometimes making a coordinate system can make the problem a lot easier to grab a hold of. Okay, so that's what I'm going to do this time. So first off, I am going to draw a coordinate system. Like so. I might not have wanted to draw it that close, but I did, so here we are. I'm going to say that right here is a distance 4. And right here, say, is a distance 3. Well, scratch that. Is a distance 3. This is your x-axis, and it's measured in meters. And this is your y-axis, and it's also measured in meters. And then I'm going to say there's another spot here that is 5. Okay. I'm going to put a point particle up here, and the charge is going to be called Q, and it's going to equal, let's call it Q1. It's going to have a charge of, let's say, 1.0 micro coulombs. Okay. This charge right here is going to be Q2, and it's going to have a charge of 0.111 micro coulombs. And this charge right here is going to be Q3, and it's going to have a charge of negative 0.111 micro coulombs. Okay. You might guess I'm trying some simple numbers here. What I'm asking for, though, is what is the force on 1 total. So notice I only have one subscript. One subscript means you're asking the force for the total force on that one subscripted item, which in this case is subscript 1. So I'm asking, what's the total force on Q1? Well, the solution goes like this. We know that the force on 1 has got to equal the force on 1 due to 2 plus the force on 1 due to 3. So again, notice the reading of that. Force on 1 due to 2, force on 1 due to 3. So that's the nomenclature I'm using. All right. We also know that Coulomb's law just says that F is equal to K Q1 Q2 over R squared, where K is essentially 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Someone else just came in. All right, so that's what we're going to use. Now, this formula only gives you the magnitude, and also it sort of makes you think that you're going to plug in negative numbers and positive numbers. I never, ever plug in negative numbers. I shouldn't say completely never. There's probably been an instance or two, but generally speaking, I never plug in the negative sign. I almost always just treat all the positives, all the charges if they're positive, and then work it out. So first off, let's calculate the magnitude of F12. So the magnitude of F12 can be written this way. F12. Notice I just left the vector symbol off of it. Another thing you can write it, just in case you're a little rusty, is you can put absolute value bars around it. But the main thing is this 8.99 is very close to 9.0, which might tell you something. So this is 8.99 times 10 to the 9th newtons meters squared per Coulomb squared. Now I've got to take charge 1, which is 1 microcoulomb, so that's 1.00, and I'm going to pretend like they're all 3 sig figs. It looks like I wrote it that way anyways, times 10 to the negative 6 coulombs, times the other one, which is 0.111 times 10 to the negative 6 coulombs. Can anybody tell me what 0.111 would be as a fraction? This is why I use these numbers.
1/9?
Yes, 1/9. So I'm using that number to cancel out the 8.99 and the K, just so I don't have to rely on my calculator too much. Okay. The distance away, which hopefully you can see, this is a 3, 4, 5 triangle. So in other words, I go to the right 3 to get to Q2. I go to the vertical 4 to get to Q1. Therefore, the diagonal is the hypotenuse of the 3, 4, 5 triangle. So this is going to be 5.00 meters. And this is why I told you guys that we're going to pretend like everything has 3 sig figs. So I just wrote 3, 4, and 5 up there. Okay, so what we see is going to happen is 10 to the negative 6 times 10 to the negative 6 is going to give me 10 to the negative 12th. But then I have a times 10 to the 9th. So that'll give me 10 to the negative 3. The 0.111 will cancel out with the 8.99. And then all left is 1 over, or 1 times 10 to the negative 3rd over 25. So this is equal to 0.2 or 0.04. Times 10 to the negative 3rd, because 5 squared is 1 over 25. If you multiply top and bottom by 1 over 25, you get 4 over 100, which is 0.04 because it's 4%. So that's why I knew that. And I already had the 10 to the negative 3rd from the 10 to the 6, 10 to the negative 6 times 10 to the negative 6 times 10 to the positive 9. So hopefully one of you can verify that this number is right, but that's basically what I'm doing. Yours will be off a little bit because obviously 8.99 is not exactly 9. So, but it should be close enough. So that's the magnitude of the force. Now, there's a lot of different ways you can actually make the force. one thing is you have the magnitude, so you could in principle find a unit vector that's parallel to the line connecting 3 and 4, and then make sure it points the right direction. So we see Q1 is a positive charge. So Q1 and Q2, both positive. So does that mean the force on 1 due to 2 is repulsive or attractive?
Repulsive.
Repulsive. So that means it's going to point from the point marked 3 towards the point marked 4. Okay. So another way you can actually make a vector is you can always subtract initial coordinates, the final coordinates minus the initial coordinates, and that'll give you the vector. So for instance, the coordinate of Q1, let's say P sub Q1, that's just giving the symbol for point. Okay. The X coordinate is 0 and the Y coordinate is 4.00 meters. And then the point for Q2 is equal to, in this case, 3.00 meters, comma, 0. Okay. So if you wanted to know the vector from, whoa, don't want to use that symbol. So if you want to know the vector R that points from 4 to, or from 3 to 4, or let's say the vector at 4 due to 3, okay, that's another way of saying it, which is also the same thing as R 1, 2, okay, then all you have to do is realize it's going to be the final minus initial, and the final, of course, is 0 minus, and the initial, which is 4, or excuse me, which is 3. And then final minus initial here is 4.00 meters minus 0. And notice I put less than and greater than symbols in there. That's another way you can specify a vector as opposed to using I's and J's. You can put it as an ordered pair, in which case the first term is supposed to be the I hat term or the X component, and the second term is supposed to be the J hat or the Y component term. And in doing so, it looks just like a point. So that's a really nice way of doing it. Now, I see that this vector, in fact, has a magnitude of 5, and we can figure out exactly what it points in, which direction it points in, because we know the 3, 4, 5 triangle. But to be honest with you, you really don't have to do any of that. Since you know the magnitude's 5, you can divide this vector by 5, and it will become a unit vector. Does everybody understand that a vector divided by its magnitude makes a unit vector? Does that make sense? So it looks like everybody's okay with that. I'm not looking at chat. Somebody let me know if they're chatting here. Let me see if I can even show chat. There it is. Okay, I can pull the chat up now. So somebody answered that. No, good job, Ethan. So R12 hat is just equal to 1/5 meters times R12. That's the definition of a unit vector, is you take a vector and divide it by its magnitude. So I'm going to say that R12 hat, that was really bad looking, is equal to -3/5. Notice the meters cancel out, comma, 4/5. So a unit vector really is a unit vector. It has no units whatsoever. It happens to be just a unit long, and that unit is just a unit of numbers, okay? So that's kind of nice doing it this way, because now all I have to do is multiply 0.04 times 10 to the -3rd, which is really, let me see, 1, 2, that's 4 times 10 to the -5th. So F12 is equal to 4.00 times 10 to the -5th power newtons times -3/5, comma, 4/5. which we can write as, of course, this is going to be 0.8. So this would be 8 times, or let me back up, 8.00 micronewtons I hat negative plus, this one's just going to be, oh, excuse me, that was not right, 8. What I was trying to do was divide by 4, or divide by 5 and be fast and loose, but as you can see, when I'm doing arithmetic in my head, that's a dangerous thing. Sometimes it works out really brilliant, and y'all look at me like I'm a genius, and then other times you're going to say, I think Mr. Younger may have a head injury, a closed head injury, perhaps. So when I multiply 3/5 times 4, basically what's going to happen is 4/5 is 0.8, and then 0.8 times 3 would be 2.4. 0.8 times 3 would be, no, wait a second, 0.8 times 3, yeah, that should be 2.4. So this is going to be negative 2.40 times, let's say, times 10 to the negative 5th newtons I hat, plus, now we're going to get the 5 again, dividing by the 4 by dividing by the 5, sorry about that. That's 0.8 again, but this time 0.8 times 4 is 3.2. So I get positive 3.20 times 10 to the negative 5th newtons J hat. So that's just one way you can always brute force compute a vector. Okay, that's not the only way. And in fact, let me show you what that vector looks like. That vector is that vector right there I just drew in black. Okay, it goes all the way, well, the R12 vector goes all the way from here to here. So you can see its magnitude really is the quantity in the denominator. And the other vector, on the other hand, is going to be, this one's a negative, so it's going to actually be attractive to that other charge. It's going to point right along here. This one is R12, whereas this one is R13. Okay. So let's go ahead and calculate our magnitude of F13. Does anybody have any questions before I go on with this? Anybody verified my math or convinced that my math was completely wrong? Because that's a real thing. It happens all the time. Anyone? Okay. So F13 is going to be, I'll leave off the units this time since we saw how it worked out before. So we got 1.00 times 10 to the negative 6. And then we got 0.111 times 10 to the negative 6. And all this will be over. This time, notice it's 5 and 4. So it's not a special triangle that we're used to, but we do know that 5 squared is 25 and 4 squared is 16. So 16 plus 25 would be 35, 41. So it's a square root of 41. And when we square it, we just get 41.0 meters squared. Okay. So we see again, everything cancels out except for the 41 squared in the bottom and the 10 to the negative 3 in the top. So I'm going to do the math real quick. 1 e to the negative 3 divided by 41 gives me 2.439 times 10 to the negative 5th. 2.439 times 10 to the negative 5th newtons. Now, I carried one extra digit. The other one, I didn't have any more digits, so that's why I didn't have to do that. But generally speaking, when you're doing intermediate calculations, I say keep at least one extra digit beyond what the significant digit rules would demand, and just keep track of it by underlining it. And then when you're done, you can underline, or you can look at where the underline is and round to the digit to the left of that, and it'll be correct as far as sig figs go in the number, but it'll also be correct in that you didn't round too much, which is often the problem when students don't get exactly the same answer in MyLab and mastering. So we now have a magnitude. We could also compute the vector, which in this case, we'd have to take 0.5 where the 5 meter is and subtract from it where the 4 meter mark is. Okay. So we can do that. We can call this R1, 3. And in this case, it's going to be the x component would be 5 minus 0. So the x component is just going to be 5 meters, and the y component is just going to be 0 meters minus 4. So that's going to be 4 meters. Now we can say that the unit vector, R1, 3 unit vector, is in fact this divided by the square root of 41. So I'm going to say 2.439 times 10 to the negative 5th newtons times 5 over the square root of 41 times negative 4 over the square root of 41. And that works just fine. I mean, believe it or not, that's actually a correct answer. It's just not the way we're used to looking at it. That being said, I'll go ahead and compute it. And because now we have to add those two vectors, but in order to do so, we need to actually basically add like components. But because we did it this way, we're already in component form. So life's pretty good. So let me write down these numbers because I'm getting ready to switch screens. I got negative 2.40 times 10 to the negative 5th newtons I hat for F12, and positive 3.20 10 to the negative 5th newtons J hat. And then F13, I got basically 2.439 times 10 to the negative 5th times positive 5 over square root of 41. I'm just writing this on a separate sheet of paper, so I don't have to go back and forth. And then the y component is negative 4 over the square root of 41. So I now have it written down. That means I can steal that when I go over there. So I'm going to go to the next page. I'll rewrite my F12. So F12 is equal to negative 2.439, or excuse me, 40. That was the one that didn't have any extra digits. Times 10 to the negative 5th newtons I hat plus 3.20 times 10 to the negative 5th newtons J hat. The F13 is a little more complicated. Actually, let's do this. I just wrote that way too close. The F13 is going to be, here's where I use my calculator. I'm going to go ahead and take 5 and divide it by the square root of 41. 5 divided by square root 41 is equal to 0.7808. So I'm going to multiply that number by 2.439. E to the negative 5. And that gives me 1.905. Actually, that gives me 1.90. I have to do 2 because the next digit is 5. So 1.9045 times 10 to the negative 5th newtons I hat direction minus the other one, which is times 2.439 e to the negative 5th. And this time I got Can't be the same. Oh, no wonder I did the wrong number. 4 divided by square root of 41. Yeah, that's what I did. 4 divided by square root of 41. I had accidentally redivided by 5, divided 5 by the square root of 41 instead of 4. Now 4 divided by the square root of 41 is 0.6247 roughly. So I'm now going to multiply that by 2.439 e to the negative fifth. And that gives me 1.524. Extra digit there, times 10 to the negative fifth newtons in the j hat direction. So now by writing it this way, we already have it in the correct coordinate format. So we can just add them like terms. I hat just acts like a x and j hat just acts like a y. You know, you can add x terms, but you can't add x terms to y terms. So F1 is just the sum of these two. So I'm going to say 1.90, and since they're all power of 10, I can just use the mantissa, which is the number to the left of the multiplication symbol. That's called the mantissa, M-A-N-T-I-S-S-A. So I get 1.9045, and I can subtract from it, since the other number is negative, 2.40. And I'll get negative 0.495. And the way this works out is this is subtraction. So we're only allowed to go to this second decimal place with this. So it's actually negative 0.50, or I could write negative 0.495. I actually have to round that to 6 newtons I hat. So I'm carrying one extra digit. In other words, let me fix that ugly thing. Okay. And now I'll do 3.20 minus 1.524. And that gives me 1.676. Times 10 to the negative fifth. Hopefully I've already noticed a boo-boo I made. Anybody catch what I forgot to write down? Times 10 to the negative fifth. Okay, so that's the total force. And in fact, we could take that as an answer, but what I would normally require is if I did not give you vectors in vector form in terms of ij's and k's, then I'd want them to come back as magnitude and direction. If I gave them to you in magnitude and direction, you could expect that I want them to come back as magnitude and direction unless I asked you specifically to do otherwise. So in this case, since I wasn't asked either way, and I wasn't actually given a vector, I'm going to assume that we want this to be returned in magnitude and direction format. And I'll go ahead and write right here that we get negative 0.496 times 10 to the negative fifth newtons in the I hat direction, plus 1.676 times 10 to the negative fifth newtons in the j hat direction. And I'm carrying one extra sig fig on both of those. Now, if I want to know the magnitude, what I'm going to do is draw my coordinate system again. Okay, and this evidently wants me to go up by about 0.5 roughly, and the other one's going to go about 1.67. So I'm going to say, let's make this line a little longer. Okay, so I'm going to say the x component is in fact going to be right about here. And the y component, notice it's more than 3 times as long, and it's actually positive. So I'm going to go all the way to say here, like that. So that means my actual F13 vector is this guy. Actually, I hate that. That turned out terrible. It makes me angry. So this is F1. Okay. And I will say this is the angle phi. So F1 equals the square root of negative 0.496 times 10 to the negative fifth newtons squared plus 1.676 times 10 to the negative fifth newtons squared. Doing this in my calculator, I'm going to say it looks like I typed everything good. 0.496 times to the negative fifth squared, 1.67 to the negative fifth squared. Now I'm going to take the square root of that. And I get 1.748. Times 10 to the negative fifth newtons. That's the magnitude. The angle phi, on the other hand, is the inverse tangent of opposite, which is the y component, which I don't have to write all the stuff. I can just write the 1.67 because the 10 to the negative fifth and the newtons is going to cancel out. And notice again, I'm also not using the signs. That actually just leads to more problems. So I always work out what coordinate I'm in and let that dictate, or what quadrant I'm in, and let that dictate what I'm going to get. So the inverse tangent of this, I'm going to say arc tangent inverse 1.676 divided by 0.496 gives me 73.5 degrees. And that's one extra sig fig as well. So I can finally say that F1 is equal to negative 0.50 newtons I hat plus 1.67. Whoa. Almost did the same mistake again. Would have been easier to erase it when I'm going back like a dummy. Okay. J hat, which is also equal to 1.75 Newton, or dang it, times 10 to the negative fifth newtons at 73, or let's call it 74 degrees above negative y axis, or negative x axis. Okay. Any questions on that?
I have a question.
Yes.
So for sig figs, does only the final answer have to have the correct amount, or does the work have to have the correct amount of sig figs too?
I'm never going to take off for me personally. I'm never going to take off for incorrect sig figs unless it's specifically a question: how many sig figs does this answer have, or how many sig figs is this answer supposed to have, something like that. But when you're working in MATLAB and mastering, if they broke a problem up into several steps, they expect it to be right significant figure wise at every step. And in order to do that properly, you still need to keep that extra digit, or at least it's been my experience that I get the most success when I keep that extra digit on all intermediate calculations. but still round it properly for MATLAB and mastering when they ask for a particular one. That being said, I also set it loose, so it's not supposed to even catch you if you screw up on that, but sometimes it still does. Sorry, I wish I could have answered that in fewer words, but I did not. I don't think I could. Do you understand, or did I make it too complicated?
No, that's fine.
Okay. Sorry about that. I tend to over explain because I'm really obsessed with being absolutely correct and direct about it, but you know, sometimes that makes it really hard. So does everybody follow what I did there? Let's look at the original problem. So we had those two charges, Q2 and Q3, creating a force on Q1. And because it was two different particles, all I had to do is say, well, one particle is going to cause one force and the other particle is going to cause another force. And what we learned is that forces add like vectors. So all I got to do is add them. But notice how I did not use the signs of the charges in the actual calculations. I just used them to decide what my direction of the vector would be. I also did something that's kind of makes it really simple to make the vector, but it's not necessarily the way that you're used to. So instead of, you know, subtracting the actual points that's marked 3 and 4 and the one that's marked 4 and 5, I didn't have to actually do that, but I wanted you to see that that was a surefire way to always get a vector. And it also allowed me the opportunity to show you how to find a unit vector, which is another thing that will become infinitely helpful to you. But what we could have done is we just could have said, okay, well, I know that the force on 4 due to 3, or excuse me, that the force on 1 due to 3 points up and to the left along the line connecting Q2 and Q1. Well, when I do that, I realize, okay, well, that line is parallel to the 3, 4, 5 triangle hypotenuse. So I can just work out what that angle is between the positive x-axis and that vector. And that, of course, if you do the inverse tangent of 4 over 3, you get 56, or excuse me, 53.1. So you know that this angle right here, let's try writing it in blue. This angle would be 53.1. So all I really had to do to get the x component, for instance, is I'd first realize the x component is negative, so I got to stick a negative sign on it. And then I just take the magnitude, which we found was 0.0400 times 10 to the negative third. I would multiply that 0.04 times 10 to the negative third times the cosine of 53.1. Okay. And then I could do the same thing with the y component, except now instead of multiplying 0.04 times 10 to the negative third times cosine, I'm going to multiply it by sine. So that's a typical way that a student finishing their, or maybe halfway through their first semester of an algebra-based physics class would do it. And probably most of the students in the, you know, halfway through the first semester of a calculus-based physics 1 course would do it. And that's fine. It's just, I'm trying to prepare you for a more generic way of working things. So just to recap, we could have said F1, 2 sub x was just F12 cosine 53.1 degrees with a negative in front of it, and F12y was positive F12 sine 53.1 degrees. Then we'd also say F13 x would be, in this case, it's actually positive because it points down to the left. It's going to be the magnitude F13 times the cosine of, and this angle, which was 5 and 4, right? So that'd be tangent inverse of 5 divided by 4. Or was it 5? Let's see real quick. No, I made it 5. Sorry. Oh, we know that's 45 then. Cosine 45 degrees. And F13y would equal negative F13 sine 45 degrees. So that's a more typical way that most students would do it. You can certainly work it that way. I'm not going to be able to tell, but we're getting ready to go into something that makes it a little more conceptually pleasant to solve problems, but conceptually also a bit more esoteric or obscure. So this method of finding vectors by subtracting coordinate points will come in handy there. So any questions on that problem now that I've given you another way of even looking at it and solving it if you so desire? All right, well, I'm going to let you solve this way for extra credit. Okay, so that'll be an extra credit assignment. I'll put it in our week 1 module. There will be a place there that you actually turn it in and it'll actually say what the problem is. So y'all can do that for extra credit. And if you looked at the syllabus already, you'll know that other than the practice test counting as extra credit, the extra credit you get this way basically just erases your lowest homework score. And I increase the number of homework scores dropped by 1 for each new one I put in. So in other words, right now it's only 1. Now, once I've created this extra credit problem, I'll drop your 2 lowest instead of your 1 lowest. So any questions on that? Okay, so let's stop sharing for just a second. I need to talk to you about something else. So we've seen how to work with these vectors using a formula that gives us a magnitude and then using either the actual coordinates of the ends and the beginnings or the actual coordinates of the actual point charges or the actual coordinates of the center of charge of the point charges. We can make vectors that way. We can also still do it just remembering that we're wanting to make something parallel to some triangle that you see on your piece of paper. So you can just figure out what the angle on the triangle is and use that to find the X and Y components. That's fine too. We're assuming at this point in the semester, chapter 21, you've already had 1 whole semester of calculus-based physics, and you've probably already had pre-calculus and the trig part of it, which obviously covers vectors or usually covers vectors, hopefully. So we think you know how to do it, but we're trying to give you a more robust way now because we're introducing vector calculus, and you really got to understand your vectors well to be able to do that. We haven't done that yet. I haven't given you anything that's quote unquote vector calculus, except for the fact that I'm getting ready to solve a problem with a vector in an integral. Okay. So here's the problem right now with Coulomb's law as it stands. Just like Newton had a problem with Newton's law of gravity, he felt that was a problem because it was like the sun was sitting here in space and had like ropes tied to the planets or something, but you couldn't find any such ropes, yet they weren't touching and they were still applying a force. That's called action at a distance. He did not like it. He had a problem with it, but he also knew that having studied it, he was able to figure out a lot of stuff. Like he could immediately explain why the sun was why the moon was in the specific orbit that it was in around our Earth. He could also explain Kepler's 3 laws of motion. In fact, he even went so far as to proving that basically any closed orbit could only be gotten by a force that's either Hooke's law, force equals some constant times the distance away, or like a 1/r² law, like Coulomb's law or Newton's law of gravity. That's the only way you get closed orbits, and those closed orbits will turn out to be what we call conic sections. So they can be parabolic, hyperbolic, elliptical, or circular. So Newton went way further than what Kepler's first law said, which was that, the planets orbit the sun with an elliptical orbits with the sun at one focal point. So he went further than that. The second law, he said it sweeps out equal areas in equal time. Well, Newton was able to show that sort of on energy methods, but really it's more like on conservation of angular momentum. And he could also show that the square of the period is proportional to the cube of the semi-major axis, which is Kepler's third law. All of that with that law of gravity. And in fact, we would be off a little bit in going to the moon and back if we don't use general relativity to take a spaceship to the moon, but it really wouldn't bother us. I mean, we could make it no problem without understanding Einstein's relativity. Okay, so Newton's law even though he knew it had a problem with it because of this action at a distance thing, he also was smart enough to realize, well, I'm not going to let that little problem bother me when I can do all this other stuff correctly. So what we did with gravity, and actually Faraday, oddly enough, was one of the people that did this. And I say that oddly enough because Faraday was the one with the very least mathematical education of all those people working in the electricity and magnetism field at the time. But he pictured it as if the space around charges had some kind of aura or field around it or something. And that was actually how the particles were interacting across the distance. So the particle exists, but it messes up the space around it, sort of like a stinky kid in the classroom. It makes that whole area of the classroom smell funny. so a charged kid in the classroom makes that whole area around the charged kid act funny. So that's what we call a field. And what a field is mathematically, it's not that complicated, but you can imagine looking somewhere in space and saying, okay, I'm going to call that the origin. I'm going to call that the x-axis, that the y-axis, and this is the z-axis. Now I've defined that so everybody knows what my origin is. Everybody knows what I consider the x direction, the y direction, and the z direction. And now I'm going to take every point in the universe and assign a value to it. So here's the point 1 meter by 3.7 meters by 2.8 meters. That's my XYZ coordinate. At this point, I declare this field has this field F has a value of 17 newtons, and do that for every, and it's not, it's not a finite number. It's an infinite number of points, but do that for every point and you have a scalar field. So for instance, if I went inside this room here and I called that corner over there, say my coordinate origin, then I could get a coordinate for every point in this room in my office. And if I measured the temperature right there and then did it for the next one and then did it for the next one and then did it for the next one and kept doing it until I got all of them done, that would be the temperature field, which is a scalar field. And the temperature field's a real field, okay? Now, you can also soup it up by not applying a number to each point in space, but by applying a vector at each point in space. So now instead of me saying there's a number 23.9 Celsius degrees at 1, 2, 3, I could now say there's a vector with an x component of 3 newtons I hat, or 3 newtons, a y component of 4 newtons, and a z component of 1 newton at the point 1, 2, 3 meters. When I do that, then I'm literally assigning 3 separate data values, one for each component, to each point in space. That is a vector field. And you can do even more. In fact, we use vector fields in quantum mechanics that are literally infinitely dimensional. So they have they literally have an infinity of dimensions. And not only that, they're not even in real space, they have imaginary space. So that's what a vector field is. So you don't have to think any deeper than that. It's just an assignment of every point in the universe a value. If that value is a scalar, then it's a scalar field. If that value is a vector, then it's a vector field. Does anybody have any questions on that? Okay, good. So imagine now, how are we going to correct that action at a distance thing by introducing this field? Well, we know, and let me go ahead and share my screen real quick so you don't have to look at me. We know, for instance, that a particular charge in a room, if it's if it's near another particle, say, it's going to feel a force. So for instance, we know from Coulomb's law that the force is equal to 8.99 times 10 to the 9th newtons meters squared per Coulomb squared. And we know that if the charge is, say, 0.111 times 10 to the negative 6 coulombs, and the other charge is 1.00 times 10 to the negative 3 coulombs, and they're in fact 1.00 meter apart, then the force, at least the magnitude, and we're going to say they're both positive, so we're going to say that they're going to be a repulsive force, you can see that the 0.111 cancels out the 8.99. And then the 10 to the negative 6 times the 10 to the negative 3 cancels out the 10 to the 9. And then the 1 squared is just 1. So I'm going to get 1.00 newtons is that force. Okay. Now, what we have done here is we basically took a coordinate system. Actually, I'm going to call that my x-axis. I'm going to call this my z-axis. And I'm going to call that my y-axis. Now, the one thing, this is kind of weird, but the one thing you have to do when you're drawing coordinate systems that involve 3 axes or more is you have to make it, well, 3 axes. You have to make it a right-handed coordinate system. So everybody see how I'm holding my hand like this? It's a very small picture, so it's kind of hard to tell. So I'm rotating it. See how I hold my right hand? My index finger is pointing out, my middle finger is pointing perpendicular to it, and my thumb's perpendicular to both of them. So if you hold your right hand like this, then your index finger, if you hold that parallel to the x-axis and then rotate it until your middle finger is parallel to the y-axis, then your thumb's telling you the direction that the positive z-axis has to go. It's not that big of a deal. It hardly ever causes you problems, but I guarantee you the first time you use a left-handed coordinate system, you're going to get off by a sign and you're not going to know why. So just always draw your coordinate systems as a right-handed coordinate system if you go more than just 2 dimensions. Okay. So what I'm going to do is now represent one of these charges with a little red dot. I'm going to say the charge is, let's say, right here. And this charge is going to be Q1. Or let's say this charge is going to be let's say this charge is going to be just Q, and it's going to be equal to 1.00 times 10 to the negative, let's say negative 3 coulombs. And I know I could have written it better than that, but I didn't because I'm a goober. Okay. So that's that particular particle. Okay. And now what I'm going to say is there's another particle over here. And that particle, I'm just going to call, let's call that Q2. And that's the one that 0.111 times 10 to the negative 6 coulombs. Okay. And I'm going to say further that this distance between them is 1.00 meters. Okay. Now, what I can do is I can pretend that Q creates an aura around it, and Q2 feels a force due to that aura and its own charge. Y'all see what I'm saying? It's like this charge Q has made some, field around it where everywhere you assign some quantity, it's actually going to be a vector quantity. And one of the points around it happens to be the point where Q2 is. And since Q2 is there, it's feeling a force. And that force is actually equal to 1.00 newtons. Okay. If you want to take out the effect that Q2 has on it, you would want to divide the force by that Q. So we're going to call the aura as the electric field. Notice I put a vector symbol over it. And in some sense, it's going to be a limit as Q2 goes to 0 of K Q Q2 over R squared divided by Q2, which ultimately just equals KQ over R squared, or the way I like to write it, as I've warned you before, R squared. Okay. Now, in order for this all to be equal, it has to have a vector quantity to it. So I'm going to just put a D vector next to each of these, and it's a unit vector, just so it's okay to write an equal symbol. Okay. That D I use because it's the first letter in the word direction. So I've made a unit vector that points in the direction of the electric field just so I can write an equality between a vector and something that was a scalar. But now by multiplying those scalars by that D vector, I've made it into a vector. So everybody understand that? Not too confusing on that one, is it? Okay, so we can see now that in reality, what you're really going to use is E is equal to F over Q, but you have to know which one it is. And in fact, you can write this as a scalar equation to get the magnitude, or you can write it as a vector equation to get the vector. But that's in practice almost always how you're going to do it. Well, the reason I did the limit thing is in principle, that aura is being created by Q, but if Q can create an aura, Q2 can as well. And because fields are actually vector fields, they add like vectors at each point in space, then that Q2 could actually cause the aura to change and in some sense make a force on itself, like, you know, lifting yourself up by your own bootstraps, which is physically impossible, right? But that's what we're doing. That's why we're being pedantic about it and say we're going to take the limit as Q2 approaches 0. We're just saying, hey, we're going to make it so that Q2 is so small that we eventually get it where it's the same answer to however many decimal places we want, no matter how small we make Q2. We just keep making Q2 smaller and say we want it to 2 decimal place accuracy. If Q2 is big and we divide the force by Q2 and the first or second decimal place changes, then we got to make it smaller. And if the first or second decimal place still changes, we got to make it smaller. And if the first decimal place stays constant that time, but the second changes, we got to make it smaller. And if we make it smaller and the second still changes, we got to make it smaller. And then finally, if we check it, make it smaller and check it again, and this time the second decimal didn't change, then we're happy. We've gone far enough. So that's sort of the mealy mouth explanation of how that electric field process goes. Now that gives us a whole new Coulomb's law. Coulomb's law says the electric field is equal to the charge causing it divided by 4 pi epsilon naught r squared, where r is the distance from the source of the field to the location that you're talking about. So in this case that we drew above, this is r. So does everybody sort of understand what I'm saying here?
What is epsilon 0?
That's called the permittivity of free space. And it's 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. If you put 1 over 4 pi epsilon naught, if you calculate that, you'll get the 8.99 times 10 to the 9th that I just told you about, for instance. Okay. And this is what most people use, is this 4 pi and epsilon naught instead of the K. People that work in engineering, for instance, or people that work in electricity and magnetism with regards to physics or any other careers, they would usually use the epsilon 0, not the K. Any questions other than that? All right, so now that we have that, we can actually derive a really nice expression, a general expression for the electric field at any particular point by using that concept of subtracting vectors that I told you earlier. So let's draw a coordinate system again. Okay. This is going to be my x-axis. This is going to be my y-axis. And this is going to be my z-axis. And first thing I'm going to do is I'm going to put Q right here. And I'm going to explain what that means by drawing some little dash marks. So in other words, this is x sub q. This is y sub q. And in fact, this is z sub q. Okay, so you can see that it's in 3 dimensions. That's just me trying to show you that it's actually in 3 dimensions. So anybody have a problem seeing what I'm talking about there? Now I'm going to put up here the point P. Okay, this is the point at which you want to know the electric field. So that's what we're trying to figure out. Well, what we have here is ability to create vectors. So this vector right here is going to be called R sub Q. And then this vector right here, which goes from the origin to the point in question, is going to be called R sub P. Can you tell me an operation you can do using RQ and RP that gives you the line parallel to the electric field at P? Anybody? Well, remember, it has to be, according to Coulomb's law, the line, the direction of the force is along the line connecting the charge, in this case, which was creating the field, and where you're going to put the test charge to feel it. So it's got to go through those 2 points. So that means it goes through the point where Q is, and it's got to go through the point P. So how can we get a vector that actually runs parallel to the line connecting the location of Q to the X that I drew?
Is it I hat?
It's actually going to have an I hat component, but it actually has all the components in general. So I need this vector right here. So I'm looking for some operation you can do on RQ and RP to make specifically this vector.
Is it a dot product?
Dot product gives you a scalar, so we can't use that, but I do appreciate you trying. So that's cool. Can you think of something else? There's 2 other things you can do with vectors. Actually, there's quite a few others, but ones that you're familiar with that you could possibly think of. Would a cross product do it? Because that gives a vector at least. I don't think it does, right? It would point perpendicular to that line because that's what it does is, two vectors can define a line if they have one common point. I mean, can define a plane if they have one common point. So that really can't be it. How about subtraction? Would that do it? Yes, subtraction is what we're looking for. I'm trying to clean this up and it looks horrible. I'm not sure I made it any better, but anyways. So yeah, what we want to do is subtract these vectors. And what we want to do is sort of consider the option of, say, the point of the electric field is that the electric field will always point in the direction that a positive charge would feel compelled to move if it was placed in it. So what we're going to imagine here is a positive charge being at that location X that we had there. And since Q can actually is a symbol, it can have a negative put in it. And if we put a negative in it, that'll flip the vector around. So that'll actually self-correct. So we should pretend Q is a positive charge as well. So I think you can see that clearly the vector head is pointing in the correct direction as I have it drawn. Does that make sense to everyone? So in fact, this vector is going to be RP minus R, and I'm going to leave a gap here. You'll see why in a second. But what I want to do is, it's kind of a waste of time to do all this fancy formula for a single point charge. So it's a lot smarter for us to do it when we're dealing with continuous distributions of charge. So I'm going to go ahead and change that Q to a DQ, and then this would be R sub DQ. Okay, actually, let's write it a little better now. Okay, so what I'm going to say is that there is a differential electric field element, dE, that's equal to 1 over 4 pi epsilon naught times dQ over RP minus RdQ. Take that magnitude and square it. Now, in principle, it's not yet a vector because I don't have a direction. So if I multiply it by that vector like I did earlier with the Coulomb's law problem for force, then that would give me the right direction. But do you see now the values change because it also has a magnitude? So I took the magnitude, which would have been like 1 Newton, say, and now I've made it bigger by 5 meters. So it's now 5 meters times 1 Newton. So in order to correct for that, I'm going to have to divide by its own magnitude. And get that. So ultimately, my formula is this, and this is one that's not in your book, but I do allow you and want you to put it on your equation sheet. Okay. So that's the equation we're going to use. And it seems complicated. It's a lot of neat, scary stuff there, but it really is quite straightforward. Let me start by showing you a problem. So what I have is I'm going to draw a coordinate system again. And I'm going to imagine that we have an infinitely long, uniformly charged wire. Okay, so here's my infinitely long, uniformly charged wire. Now in physics world, infinitely long means at least a factor of 10 larger than you are closer to it. So if you're 1 centimeter away, it better be at least 10 centimeters long, or 20, say, that way it'd be 10 from each end. But 100 we feel a lot better for, and 1,000 we really feel good with. So if we had 1,000-meter long wire and we were 1 centimeter of it, we consider that really plenty good for infinitely long. Now I'm going to say out here is the point P, and I'm going to say it's a distance r out along the y-axis. So that distance is r. It's a fixed quantity. But I want to remind everybody that this goes on for infinity that way and for infinity that way. Now the dq has a lot of different forms, and if you had my class last semester, you know that we had dm could be equal to lambda dl, or it could be equal to sigma dA, or it could be equal to rho dV, where lambda is the mass per unit length, sigma was the mass per unit area, and rho was the mass per unit volume. Well, we're going to have the same thing now, except we're going to say dq is equal to lambda dL. So it's coulombs per meter, or sigma dA. So it's coulombs per square meter, or rho dV. So it's coulombs per cubic meter. Since this is uniformly charged, and it appears to be more or less one-dimensional, we're going to say dq is going to be equal to lambda times dy. And this is a constant. And what do we mean by that? That means if we were to take, say, 1 centimeter of this charged wire and determine the charge on it, and then take that 1 centimeter and divide it by that charge, we'd get a number of coulombs per meter, or coulombs per centimeter. Then if we cut off any other part of any other length, let's say a 14.7 meter chunk of it, we cut that off, determine the charge in it, and then divide it by 14.7 meters, and then convert it to coulombs per centimeter, we get the exact same number. So that's what we mean by uniformly distributed. So I'm going to draw my little differential charge element right here as dq is equal to lambda dy. Now, according to the formula, I have to have a vector that points from the origin to P. Can anybody see if you can guess what that vector would be? Can you tell me how long it is, for instance? Or can you tell me what direction it points in? Any of those? We ain't got much time, so I got to roll on here. So here's RP. And this vector right here is RDQ. So I think you can see that RP is clearly equal to just R times I hat, and RDQ, since this is up a distance Y, is just Y times J hat. And RP minus RDQ, which is something we need, turns out to be R I hat minus Y J hat. And something else we need is the magnitude of that vector. Can y'all, hopefully y'all can see that the magnitude is the square root of R squared plus Y squared. If you can't, it might help you to see the actual vector. RP minus RDQ is that vector right there. Okay. All right, so now I can go about calculating my integral. I got to flip the page, so y'all might want to just try to render this in your head for what it looks like. So E, I did not mean to switch to green for that. I want to go back to writing in black. The electric field E is equal to the integral of dE, and that's going to be equal to 1 over 4 pi epsilon naught integral y approaches negative infinity to infinity of lambda, which is a constant, times dy times r I hat minus y j hat over r squared plus y squared to the 3/2. The half gives you the square root and the 3 means it's cubed, and we've got everything we need now. So I can further write this as lambda over 4 pi epsilon naught times the integral of, and I'm going to put curly brackets there. I'm going to say r dy over r squared plus y squared to the 3/2 I hat minus integral y dy over r squared plus y squared to the 3/2, and this one will be j hat. Okay, so I'm going to break up the integrals into parts. So I'll say I hat part. That just becomes r times the integral dy over r squared plus y squared to the 3/2. And I'm going to say let y equal r tangent theta, implies dy will equal r secant squared theta d theta, and y goes to negative infinity corresponds to theta goes to pi over 2 negative, and y goes to infinity corresponds to theta goes to positive pi over 2. Okay, so I can now say equals, the r is still going to come out in front, but now I have the integral of r secant squared theta d theta over r squared, which I can factor out of everything, times 1 plus tangent squared theta to the 3/2 power. So you see you're going to get an r squared on top, and then the bottom you've got an r squared under the 3/2 power. So that's going to make that r squared into r cubed, and then you're going to have r squared on top and r cubed on bottom. So you just get 1 over r. So I now have equals 1 over r times the integral of secant squared theta d theta. And remember, 1 plus tangent squared is secant squared, but raised to the 3/2 power means it's going to be secant cubed. So the secant that remains will be in the bottom, and that's the same thing as a cosine in the top. So I'm going to say 1 over r times the integral of cosine theta d theta. And I could actually multiply this by 2, since it's an even range of integration. Or excuse me, since it's an even function that we're integrating. I can write 2 here and then just go from 0 to pi over 2. Now, the derivative of sine is cosine, so the integral of cosine is sine. So I'm going to get 2 over r times sine of pi over 2 minus the sine of 0, which I think you can see sine of pi over 2 is actually 1. So I just get 2 over r. Now, if you look at the other integral, the j hat, you can see it's an even function, or excuse me, it's an odd function. Notice the y, if you replace y with negative y, it becomes the negative of the original integrand. And because of that, since we're integrating from over a symmetric range, this thing's going to integrate to 0. But it's also not very hard. If you look at one of my other videos, you'll see that I do take the time to integrate that. We're running out of time, or actually just ran out of time, so I don't want to do that. But it does go to 0, and you'd expect that from the symmetry of the problem, because obviously this at this point, the force or the electric field will point this way, but when you consider a symmetric dy, it'll point that way. So you can tell by the symmetry of it, the y components are always going to cancel out. So you expected a y component to be 0 anyways, but I'll just say J part is equal to 0. So now all I have to do is write E. Well, I don't want to do it in that color. And you guys are free to go. It's recording anyways, but thank you for coming, and I'll wait for the last person to leave. I'm just going to write this answer out. E is equal to lambda over 2 pi epsilon naught r, and that's going to point in the I hat direction. But in reality, since we can rotate around that axis, around the z axis anywhere we want, that means x could point anywhere. So really that r is a radial vector, and we'll say E is equal to lambda over 2 pi epsilon naught r in the r hat direction, which just means it points directly parallel to the xy plane and perpendicular to the z-axis at every point. Okay, so you guys are free to go. You can look up some other problems on my YouTube channel. That's probably the most complicated one. It's the second most complicated problem you'll do in the entire semester. It's the most complicated one so far, though, and the other ones will be quite a bit easier compared to it. So you're free to go, ask me questions. I know you have lab, but feel free to stick around and ask me questions if you have them. If not, we can try to set up an appointment later or whatever. So check out your syllabus and have a good evening.
Have a good weekend.
You too.
Have a good weekend.
You too. Anybody have any questions?
I have a question at the end. Here.
Okay.
It's just regarding schedule and class.
Uh-huh.
I was just wondering, will you be teaching this class next semester as well?
Yeah, I usually teach. I usually teach it every semester, including the summer.
Okay. Is virtual? Is this going to be virtual in the summer?
Not during the summer. Yeah, I don't want to offer that because it's going to be. This is a hard class, and it's only because students want it that I offer it online, because as you can tell, it's not trivial. But no, we'll offer an online version. I mean, a face-to-face version over the summer.
Okay, got it. Okay.
And if you're bothered by that, you can always attend my class, even though you're in this. My class meets at 9 a.m. Or excuse me, if the lab meets at 9 a.m., the class meets at 12 to 1:20 on Mondays and Wednesdays.
Okay.
Even if you're not registered, if you can find the time, you can come there and see me.
Okay, sounds good. Well, I guess I couldn't. I'm trying to think of I'm trying to work out my schedule right now. Because of the lab time that I spoke to you about last time.
Right. I also have lab hours that I use partly as office hours, and I have an office hour from 8 to 9 on Mondays and Wednesdays, and from 8 to 10 on Tuesdays and Thursdays.
Okay. Do you do you have a lecture on the off days? So not Tuesday, Thursday?
Tuesday, Thursday, this is the only lecture I have.
Okay. Other than Tuesdays and Thursdays, do you have other lectures other days?
Yes, I have the 242 class. Actually, I told you wrong. I said it was from 12 to 1:20. The 242 class is actually from 2 to 3:20.
Gotcha. But those aren't virtual, correct?
Right. Those are face to face in JC 13, I believe.
Right. Gotcha. Okay. Yeah. My main issue is I have to do an hour and a half commute.
Yeah, I feel you. I'm driving an hour myself.
Yeah. So I'm trying to find the best way to kind of navigate around my schedule right now.
Most students they'll actually go and go in the computer lab or one of the labs in the physics department and do the lecture portion and then go straight to lab after that, because it's real hard, almost impossible for someone to make it from home in the
Right,
2-minute slot we give you.
right. Okay.
But let me know
Alrighty.
how I can help you. And like I said, it's not a big deal if you have to leave early or late. You're always going to have the recordings should always happen. And I've always got old recordings in case, something happens to that one.
Okay.
And visit me. I mean, like I said, I don't want to force you to only interact with me through these videos. So you're welcome to see me, or we can set up Zoom sessions where it'd be one-on-one, or we can
Mhm.
set up Zoom sessions where it's a group study group thing.
Okay.
So I'm not, I'll let you know if if I don't have the time. Just know that it's because I don't have the time, not that I'm being mean or something.
Sure. Of course. Understandable. Well, I appreciate that very much. I think there's another class that I might be able to take. It's a completely different class.
Mhm.
And I might have to replace this one with that one. That's kind of where I'm at the moment.
Gotcha.
Because the other class, it doesn't require me to be in a lab.
Oh,
It's math, yeah. So it's the lab portion that's really getting me right now. So
gotcha.
and drive,
Well, we have
but
other lab times too, if that could help you.
right,
I offer a lab on that's actually at 9 in the morning on
right.
Wednesday is the
Hmm.
lab for this class.
Hmm.
So you could attend that if you'd like to, and we could do it off the books if it's not, if it's something that you can't do according to the books, we could do it off the books. I don't mind doing that. Just to help you out, or you could do it, as needed. Sometimes the
Right.
student will come into my lab instead of their own lab, and I'll let
Hmm.
the other teacher know.
Right.
So just let me know what I can do to help you. I'll work with you.
Okay. All right. Sounds good. I'll shoot you an email once once I make a decision.
Okay,
I'm
I do
trying
promise
to.
you, everybody in the class, save maybe 1 or 2 people, feel that this is brutal,
Uh-huh.
like you do, and they get scared, and that happens every semester. And out of a class of 30, I sometimes get one person that doesn't pass, and
Oh,
usually
okay.
I do get that. So
Right.
just hang in there. If you have to take this, hang in there. We can get you through it, and we can get you through it with even a decent grade. It's just
Okay.
going to require some work, and I'll work with you as much as I can.
Right. Okay. Sounds good. Yeah, I mean, if I had to take this class, I would like to take it with you, just because I've heard a lot of good things. Um, so I'm trying to, but I've also had a good experience with my math professor as well.
Right.
And so I'm
Is your
trying to kind
math
of
teacher
balance
Miss
things out.
Krasevsky or Miss
Yeah,
Dale?
yeah. So I'm trying to weigh the pros and cons right now, and yeah. Are you going to be teaching this in the fall?
Yeah, I teach it every semester.
And is it virtual? Will it be virtual in the fall as well, or no?
I teach a face-to-face and a virtual every semester.
Okay, just not in the summer.
Yeah, in the summer I teach a face-to-face, but not a virtual. Yeah.
Got it. Got it. Got it. Okay. Um, I guess the thing that's going through my mind right now is maybe I'll save the lab classes because I do have another circuitry class that I have to take.
Mhm.
And there it requires a lab as well. So it
Okay.
requires a drive. So I think maybe I might push any classes that require a lab to just take it all at once. Um, so I'm not making multiple drives, multiple semesters, if I don't have to.
Right.
Um, I think I might do that. That's kind of where I'm leaning towards at the moment.
No problem.
I'm not
Yeah,
quite sure yet.
you gotta find out what works for you, and that's you'll be fine. You can make it. You could just live homeless. Just be homeless for the semester and camp out
Yeah.
behind the building and walk in and out from time
Yeah,
to time.
yeah, that's an option. Um, okay. Well, we'll see. Maybe
No
I'll
problem.
do that. Yeah. But I
All right,
appreciate
like I
your
said, just
help.
let me know. I'll be glad to help you. And I
All right.
know it's scary, so don't get too fretted. I know you could pass it if you have to, but you do what's right for you, and it'll be cool. I understand.
All right. Well, thank you, Professor.
No problem. I'm
Appreciate
going to
it.
go ahead and finish that other integral, and I'm just going to put it on the video and save it so
Okay.
everybody can see it. But you're free to go.
All right. Sounds good.
Have a
Thank
good one,
you.
man.
Yeah, you too. Thank you. Bye-bye.
Bye bye. All right. I want to go ahead and do this integral because I usually don't like to leave integrals. From the symmetry of the problem, I think you can see if you look at the point y that I have drawn in this bottom diagram, the one I'm pointing to right now is this guy. Okay. Well, if we consider the symmetry, the symmetrically equivalent spot on the other side right here, you'd see that that would create an electric field vector like this one. And you see by the symmetry of it, it's the same distance away. It's the same distance along the y-axis. It's the same distance along the x-axis. Therefore, the angle is going to be the same. And since it's the same distance away, the magnitude is going to be the same. So that means that top vector has exactly the same x component as the bottom vector, but that top vector has a positive y component, whereas the bottom one has a negative y component that are equal in magnitude. So those two equal in magnitude but opposite in sign y components cancel out. And physically, for that reason alone, you would expect that to mean, oh, this is not going to have a net y component. And that's what I basically told you by arguing that the argument of the integral, the actual integrand, was what we call an odd function, the archetypal odd function being like the sine of x function. And since it's an odd function and it's integrated over a symmetric range, that means that the right-hand side is going to be one sign and the left-hand side is going to be the other sign, and they're going to cancel each other out and give a total of 0. So that's the mathematical reason why. And that's just understanding functions and how they behave. But I'm going to go ahead and work it out brute force with the integral, because it actually turns out to be a fairly easy integral to do because we have that y on top that makes it all easy. So I'll do that, and then I'll explain a little bit more about even and odd functions and just put it on here so everybody will have it. So here we go. So the j part that I skipped, I'm going to go to now. So actually, I shouldn't write j part that way. The j hat part. So this integral turns out to be just I'm leaving off the negative, it's just the integral of y dy over r squared plus y squared to the 3/2. This time I am going to say let r squared, or excuse me, let u equal r squared plus y squared, then du will equal 2y dy. So I'll need a 2 up top, but I already have the y, so that's why this one's an easy integral. So I'm going to multiply it by 2, but I'm also going to multiply it by 1/2. So there's my that, and now the 2 will cancel that 1/2 out, and it'll become 2y dy, which we said was du, and then that's all over u to the 3/2 power. So that integral is super easy. Basically, we're integrating u to the negative 3/2. So if you take negative 3/2 and add positive 2/2 to it, you get negative 1/2. And then you got to divide by negative 1/2, which is the same thing as multiplying by negative 2 times u to the negative 1/2 is what the integral becomes. So that negative 2 times u to the negative 1/2 is what the integral becomes. Now I'm going to plug back in what u is and use the regular infinity to negative infinity to make sense of it. So at this point, I'm going to say we now have a negative of square root of r squared plus y squared in the denominator, evaluated from y approaching negative infinity to positive infinity. So I think you can see the limit as, actually, let's not do implies here. Let's do the actual equals. Okay, so what's going to have to happen is I'm going to have a negative 1 here, and then I'm going to take the limit as y approaches infinity of 1 over square root r squared plus y squared minus the limit as y approaches negative infinity of 1 over the square root of r squared plus y squared. And obviously, or hopefully you can tell, obviously these are both 0. So it's going to be the integral is going to end up being 0 minus 0. So we ultimately get -1 times 0 minus 0 equals 0. So as I claimed, the y component of this force will, or this electric field, will actually work out to be 0. If I wanted to soup this problem up and test whether or not you really understand how to do it, I could give you the similar problem, but maybe let the wire, instead of going all the way to positive infinity along the y-axis and the negative infinity along the y-axis, I could let the top part go, say, to 10 meters and the bottom part go to, say, 40 meters downward. And in other words, down to -40 meters. That would make a lack of symmetry that would not allow the y component to be canceled out, and you'd actually get an answer. So that's a real thing that you could possibly do if you want to soup this up a little bit. You could also compute it where it is still symmetric, but maybe it's only, let's say, runs from -10 meters to +10 meters. And then you could, calculate what the electric field is at 1 centimeter away, and then calculate it at 10 centimeters away, and then calculate it 1 meter away, and stuff like that, and just see how good of an approximation these individual functions that we derive, these electric fields that we derived, are for being like they are when we treat it as if it was infinitely large. So you can compare the infinitely large result that we just got, which is lambda over 2 pi epsilon naught times r, to what the actual formula is when you don't assume it's infinity and you just integrate from say -10 meters to +10 meters, or -100 meters to +100 meters. So those are all things you can do to try out other things like this, to get practice like this. Now, what I wanted to mention to you is the odd and even. So just because that's something that comes up from time to time, and students don't necessarily get it that well when they're doing it in calculus. So it might be worthwhile to show you a little bit. So the typical scenario is you have this axis like this, and an odd function is one that looks like the left-hand side looks like a mirror image of the right-hand side. So a very typical example of that is y equals cosine is a case of, well, I guess it tried to do this is a case of an even function, y equals cosine. So if I go like this, and then I do the same thing on this side, that is y equal cosine x, and that's what we call an even function. So if we actually integrate over let's say a symmetric range, which would be from here to, say, here, you can see that this area is the same as this area, and that this area, if the thing was drawn very well, is the same as this area, so that you just could integrate from 0 to L and multiply it by 2, or you could do from -L to L. However, if you had an odd function, y equals sine x, okay, draw our coordinate system again, hopefully a little neater this time. Of course not. Okay. And hopefully a little better graph this time. Sine looks like this somewhat. Okay. Again, you can see in this case, the area under here is positive. The area under here should be, if properly drawn, the exact same area, but negative. And if we went to symmetric ranges, say, then you'd see that, in fact, these two would cancel out. So the integral from -L to L goes to 0 for this. Also, if you took the time to actually do a Maclaurin series expansion, you would see that cosine theta is actually equal. We call it an odd function. The reason why we call it an odd function is this. Actually, that one's supposed to be minus. And y equals sine theta turns out to be theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus dot dot dot. So that's where the naming comes from, as well, as because odd functions act like functions whose x value is a even power as an odd power, and even functions act like functions whose whose variable x is actually an even power. So anyways, hopefully that helps. You can use that trick a lot whenever you remember, whenever you integrate over a symmetric range, if it's an even function, then you can multiply it by 2 and just integrate from 0 to infinity, or from negative infinity to 0. Either one will be fine. If it's an odd function, then and you've got an even range, you can automatically just call that integral 0. So I hope that helps. I'm sorry these drawings didn't come out better. I was drawing it and like with my elbow up against the book, so I'm making jagged edges, but have a good day.